Okay, so functions. I can't even speak. Okay, functions and graphs. So, the main things that you need to recognize when you're asked to draw a function, or if you're looking at a function, are these things. So, axes intercept. So, where does it cross the x and the y-axis? Gradients. If there are any gradients, specific gradients, you need to recognize those. Turning points, maximums and minimums. We've discussed those at length. The values of x where the functions do not exist. Okay, so in other words, are there any asymptotes? So these 2 points are joined together. The functions we need to recognize include, actually, you don't need quartic. Ignore these, covered already. But we have covered exponentials, we have covered log graphs. So this is the one that we need to focus on now. I will discuss cubics as well. Okay? So linear, yeah, y equals mx plus c, it's a given. Quadratic, I've talked about this enough. They're all parabolas, they have a maximum and minimum point, and the highest power of x is going to be 2. Cubic graphs, so I'll slow down a little bit here. So cubic graphs, for these, the highest power of x is going to be a 3. Now, if you just have y equals x cubed, then it will look like that. Okay, so it goes through the axis at 0, 0, and it looks like that. If it's negative x cubed, it will go the other way, like that. Okay, now that's if it's just x cubed. If it has anything else in it, so if it has the bx squared plus cx plus d, or anything of any combination of those, then it's going to look more like this. So if a is positive, then it will go up, then down, then up. If it's a is negative, it will go down, then up, then down. That's the key thing there, I guess. Depending on where it's placed on the axes, so for example, if the axes are here, you'd have 3 x-intercepts. You'd have a minimum point and a maximum point, and you'd have 1 y-intercept. Okay, so they're the kinds of things you need to look out for cubics. And this is just a little snippet from a textbook. Okay, so we can see that they're either the more bumpy or the flat in the middle. If you have it in this format, which is not often, to be honest, but the rules apply that we've learned already for transformations of graphs. We know that a number inside a bracket tells us what kind of movement is happening. Horizontal. So this would move to the right by h units, so across h units. And the plus k tells us what about transformations of functions? Pardon? Vertical translation, and in that same direction. So if it was minus h plus k, then it's going to have moved through this vector hk. Remember, the top number tells you your horizontal movement, and the bottom number tells you your vertical. If it's in this format, then I'm hoping you would appreciate it's very similar to quadratics in that if it's already factorized, this value, and this value would be your x-intercepts. Yeah? In some cases, you may have a quadratic that would look more like this. Okay, and in that case, it just touches at this point and crosses at this point. This is all connected to the quadratic work that we did, because if we had y equals x minus 3 squared, we know that just crosses at 3 and is our parabola. So if you have any feature of that within the cubic graph, then it's going to be the same thing. It just touches at that point rather than goes through it. Okay, any questions? No? So cubics and parabolas are often linked together. Like You don't really need to learn a lot more about cubics than once you've established everything about quadratics, which we have done so in depth. Okay, so this is the main one that we're going to focus on at the moment because I haven't gone through it with you yet. So, reciprocal graphs. So they're in this format where you have some kind of number, and look where A is. A is on the bottom of the fraction. Okay? I don't mean A. X is on the bottom of the fraction. So if X is in the denominator, it means that we have a fraction, but we know that we cannot divide anything by 0. Which means that if we just had a basic, for example, y equals 2 over x graph, that the asymptote, which is where the graph never touches, would be, sorry, the vertical asymptote would be where x is 0. Okay? That is because we cannot have 2 divided by 0. It's impossible. Now, what that means is it's very difficult to sketch it on a diagram because the line x equals 0 is what kind of line? What do we normally call the line x equals 0? The y-axis. Okay, so this is actually the line x equals 0. Okay, so our vertical asymptote will always be of the equation x equals something. Okay, so they're the vertical asymptotes. And it will always be determined by the denominator of the function. Okay, so we look at the denominator, and that's what's going to determine what the vertical asymptote is. The horizontal asymptote, this one here I would hope you would be able to see. If it's just a basic graph, it will be at y equals 0. We can see that the two branches of the graph get very close to the x and the y axis, but they never actually touch it, indicating that they are our asymptotes. I'll talk more about how to find the horizontal asymptote in a second. Actually, no, I might as well do it now. So in any stage, to find the horizontal asymptote, in other words, the y equals 1, what you would do is you would substitute a very big number or very big value in place of x. Now, why would we do that? Well, what's happening is we're saying to ourselves, what's happening to the graph way out here in the distance? Okay, so we're saying what's happening way down there. And if we do that, we can see where the graph goes to. Okay, and the words we usually use are where it tends to. So if we go back to the y equals 2 over x situation, if we had the value of x as 1,000,000, 2 divided by 1,000,000, if you do it on your calculators, it would probably round it to give you 0. Okay, so what we're saying is that if this was a massive value, then the 2 kind of becomes insignificant, and it's just going to end up being close to 0. Do you follow that?
Should we always use 1,000,000?
10,000 million, like depending on, I mean, yeah, just use a big number. Okay, sometimes you can get away with using 1,000. They tend to all give the same value. No, they do give the same value. So if you're not 100% sure that that's right, you could also put in a very big negative value. Okay, and that should also give you the same answer, because what's happening is that this portion of the graph is getting close to it here, and this portion of the graph is getting close to it here, but they both tend to the same line. Okay, so they both tend to the same value. So all you have to do is to stick a big value in place of your x and see what number it comes up with.
So you do 2 divided by 1,000,000?
Yeah.
And then see what that does.
Right. So as x gets very big or very small, the value of y gets closer and closer to 0. And that's because they are asymptotes. because y equals 0 is asymptote. Now we very rarely see functions just as basic as a over x. Normally they're a little bit more complicated, but the principle would still be the same. In this case we've got a fraction and then we've got plus some value. It doesn't matter how it's given to you as a function, the rules are always the same. For this one, our vertical asymptote would be at the value of x equals h. In this case, that's because that's when we know that x minus h cannot equal 0, and so x cannot equal 0. X cannot equal h, which means that x equals h is our vertical asymptote. So x minus h cannot equal 0 because it is our denominator. So rearranging this, it means that x cannot equal h. So if it cannot equal h, then that means that that's its asymptote. Okay?
Is that always, is x always h, if it's like that?
Yes, if it's in that format, yeah. If it had said 3 over 2x minus 5, then your asymptote would be at x is 5 over 2. Okay? You're just saying what makes the denominator of the fraction equal to 0. Now looking at this is a combination of the transformations information work that we've done. So we're fine with that one. All of this minus h would have done what to the function if we've got minus h instead of just x? Moved it to the right. So we know it's a shift to the right, which is also working well with this because our asymptote was originally at x equals 0, now it's gone to x equals h. Well, what does the plus k do to a function? It shifts the graphs up or down, yes. And so where our asymptote was at 0, it's now going to have shifted up to k. Okay, so that all is combined, and it's really important that you don't see these things as separate topics, that they are all intermingled, and some of the transformation work can help you work out some of these values. But if you wanted to know the specific value of k, as I said, you would just stick a very big number in place of the x, and that would tell you what the value was. Now, if you were asked to sketch the diagram, you can sometimes just see from your calculator what the value is. You can see, you could see that there's a gap here. You'd be able to read what the number was. Sometimes if they've given you a diagram, again, you can see which value it is. You don't necessarily have to do the substituting numbers in. Always try and have a guess before you do these things, so it will help confirm it once you actually stick it in. So have a look at it, think, okay, what do I think it might be? Let's see if that's right. Okay, so this is all explaining that. The denominator of fraction cannot equal 0, blah, blah, blah. Okay, and so the horizontal asymptote is given by the value found when substituting a very large value for x. Okay? Let me just stop that.